is actually a review presentation, nothing new that you should know about, but it's a kind of reminder about the IGS contribution to the IRF. And for this presentation, I identified 5 key points where IGS contribution to the IRF is fundamental. So you have these 5 points, key points listed, and I will go through these and illustrating the result from IRF 2014. Just to start with some statistics, we have 20 years and 22 years for GNSS and DORIS in terms of time span, 35 years for SLR and VLBI. So keep in mind that the IGS reference frame depends heavily on SLR and VLBI and also DORIS to actually distribute the reference frame for other applications. And you see that this proportion of number of sites per techniques between GNSS and the 3 other techniques. This is the network of the IGS network that is included in the IRF 2014 based on Repro 2 campaign. And I will come back to that later. Here you have this map that shows the total number of collocation sites that we used in the IRF 2014 construction. And if you take the 3 other techniques by pairs, SLR and VLBI, we have only 11 sites, but still with a decent distribution in terms of geometry. We have 11 for SLR DORIS, and VLBI DORIS 12 sites. So I will be talking about how, if we construct an IRF-like solution using SLR and VLBI alone, compared to IRF 2014, and then you will see the contribution of the IGS network. Here are the total number of local tie vectors. From GNSS to DORIS, we have more than 100, which means that DORIS is contributing to the geometry of the network. 56 for SLR, 62 for VLBI, and in total we have 221. So for the first key point about the orientation, you know that we have to ensure the alignment of the successive IRF solutions in orientation. And for that, we have to select a network, and that network that you see here is what we selected for the IRF 2014 alignment to IRF 2008. And you see that the GNSS sites are much, the number is larger than the other 3 techniques. One point that you can also ask, what is the frame uncertainty when you do that combination? And to do that, these are not only the values, but in red, what I put here are the uncertainty, and you have to keep in mind that these are formal errors representing or reflecting the geometry uncertainty of the frame realization. So we are at the level of 0.2, 0.1 millimeter, and same millimeter per year for the rate. Now, imagine that if in order to study or to evaluate the frame uncertainty, you can construct an SLR VLBI alone frame using 16 local ties in 11 sites, compared to 221 local ties for the full IRF 2000 combination, where we used also, of course, full SINX files for these local ties. And this is the two lines of the uncertainty, of the frame uncertainty. And you see if you look to SLR and VLBI alone, compared to IRF 2014, you have a factor of 2 improvement in terms of formal errors. These errors represent the frame uncertainty of VLBI frame within that combination, either SLR plus VLBI alone or the IRF 2014 itself. Now, another frame parameter, which is highly important for scientific application, is the scale factor. So I will be starting by showing the scale factor that you can estimate when you combine SLR plus VLBI alone using these 16 local type vectors, but with a decent distribution in terms of geometry. And this is 1.02 ppb. And look to the uncertainty, which is 0.2. Compared to ITRF 2014, you see that we gain a factor of 2 in terms of precision of that scale factor parameter determination. We innovated for the ITRF 2014. As you know, we estimated annual and semi-annual signal and also modeled the post-seismic deformation in order to actually improve the accuracy and the robustness of the ITRF 2014. And GNSS is heavily contributing to the post-seismic deformation modeling. And for that, as you know, we actually fitted parametric models using uniquely GNSS GPS data or time series at major earthquake sites. And for sites which are co-located with the other techniques, we apply these fitted models to the other 3 techniques using these 4 parametric models. Now, just to give you an example for Tsukuba trajectory, here you see in red, I think you will see that, for the 3 component after the earthquake, the post-seismic deformation is very strong, and the model fit not only GNSS marker, but also VLBI, which proves that these models are also consistent with the other techniques and make them to be compatible within the ITRF 2014 solution. Another key point of IGS contribution is when we determine the ITRF 2014 plate motion model. We start, of course, by the full picture of velocities of the velocity field, more than 800, and then we have to discard all sites located at boundaries, plate boundaries, and deformation zone, and do some criteria selections, and we ended up with 297 sites located on 11 plates. And all of them are GNSS sites. And some of them are co-located with the other 3 techniques, which means that the other 3 techniques contribute to the velocity estimation of these sites. And this map shows you the residuals of this fit to determine the plate motion model of the ITRF 2014. And we are quite happy with that model. And as you see, the WRMS are at the level or better than 0.3 millimeter per year, which is much more precise compared to what we had with the ITRF 2008 5 years ago. Now, another example of GNSS contribution is polar motion. And what I am showing here, the plots that of the post-fit residuals for the 4 techniques, VLBI here, SLR, IGS, or GPS, GNSS actually, I should say, and DORIS. And as you see how GNSS polar motion is dominating the other techniques. So we can conclude that, and we know that GNSS is providing the most precise polar motion estimation. The 5th example is actually the IRF Access. We build the IRF not only for science. Of course, it is important for science, but also for practical geodetic applications. And for that, we need, of course, product, because nowadays, in order to construct national reference frame, we do that via GNSS. No SLR, no VLBI, no DORIS. But of course, the reference frame depends on those 3 other techniques. So we are using, not me, those are who are constructing national reference frame, for example, they are using IGS product. Just to illustrate that, I have this map from Jeff Blewett, which goes back to 2014, and I will use his expression by saying that GNSS exponential data explosion. He is processing these more than 13,000 stations every day, I think, at the Nevada Geodetic Laboratory. and he picked all the GNSS data from local, national, and regional networks. Of course, he is also using not only the original data of these RINEX files of these sites, but also the IGS products, which are fundamental. And we can see that the GNSS and IGS actually provides universal access to the IRF. And to illustrate that more, here is, I am coming back to the GNSS network, to the IGS network within the IRF 2014. We have 884 sites, and this will facilitate the alignment of GNSS-based frames to the IRF. I mentioned the national reference frame, but there is also another application, and I am greeting the ICG Working Group S in room number 326, who are following this presentation, just to remind you that the reference frames that are associated to the provider GNSS systems, they are using also IGS products to align their reference frame to the IRF. So if you think about PZ90 for GLONASS, GCS Chinese reference frame, and Japanese one, and also the GTRF, which is the Galileo terrestrial reference frame, they are all aligned to the IRF, and also we use, of course, IGS data. Just not to forget to mention that 80% of the national reference frames are aligned to the IRF, and the source of that is we sent a questionnaire within the United Nations Global Geospatial Information Management to the countries, and 80% of them said the IRF is important for them, and the IGS products are also highly critical for their application. So I will leave you with these key points, the 5 key points. There might be others, I am sure, about the IGS contribution to the IRF, but keep in mind that the reference frame itself depends heavily on SLR for the origin and SLR plus VLBI for the scale. Thank you very much.